Hi, it's Graeme Cox again, and thanks for joining us in the third video of this training series on GPS landforming. In the last video, we covered the equipment that you need broadly, and then we looked at a case study field that required one-way drainage. In this video, we're going to look at some more case study fields and look at the other two surface types that we can use when designing our fields. And then we'll all speak to some farmers that have used this technology and got great results from it. Before we head to the computer, I just want to explain the background that we're looking over here. This is the Burdekin River irrigation area, and it was converted to irrigated cropping over the last 40 years. Before that, it was cattle country. This is where my grandfather and his father, etc., ran cattle. It was converted to irrigated cropping with the help of laser grading. And that involves significant earthworks. If GPS was around then, we probably could have done this with half the earthworks and a lot less topsoil movement. So the Davco home farm is this area here, which is from that road there to this drain here, and it goes, so that's about 2 kilometres or 1.25 miles, and it goes back about 10 kilometres or so it's 6 miles. And so that's about 5,000 acres there, and that was all done with laser grading. You won't be able to see it, but right back in the distance towards those hills, that's where the new farm is. Might be a small dot on the horizon. That's the new shed there. That's why we developed OptiSurface, because there's another 10,000 acre farm over there that we're developing. That we didn't want to shift all the earth that we shifted here on this farm, and GPS enables us to do that. So that's why we're here. Let's head to the computer and look at some more case studies. Okay, before we head to the computer, I want to start with a whiteboard session so we can cover off those surface types in a bit more detail. Okay, so here we are. We've got our 3 surface types listed, and we'll go through them one at a time. First one way, is applicable to any field that's got furrows and beds in it, and you want to drain the water in one direction. So particularly required for furrow irrigation, where you're putting water in the top end and it's flowing down the bottom. It can also be used for bay irrigation. The basic requirement is to get the water from one end of the field to the other. Okay, so if we look at a profile view of that, we've got, the water is just basically flowing downhill from one end to the other. Okay, for two-way designs, it's applicable for crops that are still grown on beds and furrows, but they don't have to drain from one end to the other. And this is typically the case where you've got a field that's got some ridges and some valleys in it, or lower spots, and the furrows will actually drain off the ridges into the lower spot, and then you'll have a cross drain coming across the field. And that's what I've indicated here. So we've got the green arrows indicating the flow of water in the furrows, and then we've got a blue arrow here to indicate a cross drain that's going to take water out across the field. And this red line here indicates a ridge. So that's a high point in the field, natural high point, that we're going to drain water away from. And our last surface type is a 4-way, and that's when you're planting on a flat surface and you don't have any furrows to restrict the flow of water in any direction. So the water can meander its way off the field. Now, it's typically for rain-fed grain crops like wheat, corn, etc. But it's also often used for pivot irrigated crops as well. A plan view of that looks a bit like this, an example here, where water is meandering its way off the field. As long as there's no depressions in the field where water can lay, the water has to get to the edge of the field, and then the software assumes that you're going to take care of it once it gets to the edge of the field. So if you've got a ridge here that won't let the water flow out, then you need to install a drain down this side to take the water away as well. I've drawn a blue line here to represent a flow path that we'd like the water to flow. So we can define what we call a valley zone in that area, and the water will act as a lower spot in the field and drain the water away from it. I've also put a ridge here, that red line representing a ridge, so that if we didn't want the water to flow at that southern boundary of that field, we can define that, we can draw a ridge zone in that area, and it'll actually act like a ridge and force the water to flow back the middle of the field. And we can put those ridges anywhere in the field, on the edges or through the fields. So we can force the water to flow in the directions that we want. Whenever you force these extra requirements, the earthworks will go up. It'll either stay the same or it'll go up. So in this case, we might require some extra earthworks, extra fill in this area to force the water to flow in that northerly direction. Okay, hope that's given you a good overview of the different surface types. Let's go to the computer and look at some examples of the two-way and the four-way. For our case study on a two-way design surface, we're going to look at a centre pivot in Africa. It's 69 hectares or 173 acres. This centre pivot will run over sugarcane grown on furrows. The centre pivot is on a greenfield site and requires reliable surface water drainage to allow timely machinery access and operations and less compaction, particularly during mechanised harvesting. Now here's the existing topography. There's a high ridge that runs along this direction here, falls off either side. This colour scheme on the legend here is actually different to all the other maps you'll see from OptiSurface. We actually switched this around to have red up the top and blues down the bottom. Here's the inputs that went into the calculation. So we set the surface type to OptiSurface two-way. We set the main slope direction to 292 degrees. That's the direction the furrows will run. We set the calculation grid spacing to 10 meters and the cut fill ratio is 1.2. We'll look at the boundary first, which is effectively the whole field. So the main inputs are minimum grade of 0.1% in the main slope direction, maximum of 1%, a smoothing of 0.2%, a cross slope of -1% and +1%, so this cross slope can go in both directions, and a smoothing factor on that as well. Now there's one subzone in this design, and it had a special zone setting of ridge. So this is the resulting proposed topography that comes out of the calculation process. This purple polygon here is our subzone that we defined as a ridge. So that tells the software to make this the highest part of the field for each row, and the rows are running in this direction here. So if you looked along this ridge, it would be the highest point along any of these rows either side. Now if for argument's sake we put another subzone in this area here and we define that as a valley subzone, that would drain off this ridge to that valley, and then this edge would actually have to drain back towards this valley, so that would all be falling backwards. Obviously that's not what we want to do in this case because the land is naturally sloping in this direction. If we look at the cut fill map, we can see there's cutting and filling spread over the field, getting rid of a few knobs. Now if we didn't do these earthworks, water would be pooling all throughout the furrows because it couldn't drain out. If we come back and look at the earthworks, in this case we had about 23,000 cubic meters of earthworks. That comes out at 338 cubic meters a hectare, which is roughly 60 cubic yards per acre. To show you what this looks like in profile, I've drawn a couple of cross sections through this field. So here's the long section along the direction of a furrow. The black line is the existing topography and the blue line is the proposed topography. So you can see the blue line, which is our calculated surface, follows the natural topography as closely as possible, but it's cutting and filling in small amounts to get our result. Now the vertical scale on this is exaggerated. It is flatter than this. Here's a cross section that's perpendicular to the furrows, and you see it's because we had the cross section slope set to plus and minus 1%, it's actually, the slopes are positive and negative, as in they can fall in both directions, but it's still following the natural topography as closely as possible. One more comment in this design. With these slope constraints here, we ended up with 338 cubic meters a hectare. Now we generally apply smoothing and a maximum slope constraint to get the slopes as uniform as possible while trying to keep the earthworks at a reasonable level. If we removed all of these constraints here and just kept our minimum constraint of 0.1%, we can actually halve this earthworks. And we wouldn't recommend it for a couple of reasons. We think the smoothing and the maximum slopes improve irrigation and rainfall infiltration uniformity, and it allows the earth moving machinery to follow this design more correct, and obviously for machinery access such as harvesting and planting, you'd like a smooth surface to work with.
I hope that's given you a good overview of how the OptiSurface two-way surface type works. If you've got any comments or questions, please put them in the input box below. Okay, so the case that I'm going to take you through for a four-way design is called Mooney Moonscapes. It's located in Mooney, Queensland, Australia. It is 133 hectares or 333 acres. No irrigation occurs on this field. It's all dry land, rain-fed, with no furrows. Crops are generally wheat, cotton and sorghum. So this field has naturally many small gilguys or craters, which are typically 30 metres or 90 foot wide and 0.3 of a metre or 1 foot deep. The gilguys severely limit surface drainage, which makes the field marginal for cropping. Ponding analysis shows 14% of the field experiences standing water. This creates waterlogging problems for crops in these areas, but also delays timely machinery operations for the rest of the field, waiting for the ponded areas to dry out. Also, the steeper edges of the gilguy approach 5% slope. This increases runoff into the bottom of the gilguys and reduces infiltration over areas of the field, therefore reducing the crop yield of the field even further. Using the drainage analysis tool in OptiSurface, we can calculate a ponding map like this. It shows the depth of water standing in the depressions. You can see there's a lot of small depressions. Most of them are less than 1 foot deep. To show you what that looks like, here's a harvester in that field now. And here's sorghum being harvested in another year. You can see the ponding problems it creates are massive. We ran some numbers on the typical costs of this poor surface drainage. So first of all, yield loss from the waterlogged areas. Let's say there's an average reduction of only 25% over that 14% of the area that ponds water, and that's a conservative number. With a field area with a gross income $2,000 per hectare from cotton and wheat rotation, that's about $9,000 per year. A yield loss from less timeliness of planting and harvesting, say an average yield reduction of 5% over the remaining 115 hectares of this field, gives us an average cost of $11,500 per year. And then if we look at the yield loss from reduced infiltration uniformity, let's say an average yield reduction of only 5% over the remaining 115 hectares of the field, that gives us another cost of around $11,000 per year. So if we add them up, the estimated average cost of this surface drainage problem is $32,000 per year. So what's the solution? We do an OptiSurface four-way design with a minimum grade of 0.5% to promote surface drainage, and then we set a maximum grade of 1% and a maximum rate of change of 0.05% per metre to promote more uniform infiltration of rainfall. So if we look at the design, here's the proposed topography after we've done the design on it with those input parameters, and you can see there's no depressions left anymore. It's quite an intricate design with water flowing in different directions to get the water out of the field. So you see there's a couple of high spots, but there's no depressions anymore. Every part of this field is draining with a positive slope towards the edge. And if we look at the cut fill map, we can see the depressions filled in and cutting beside them, off the high spots beside them, filling. So this is quite an effective earth moving operation because you're often just cutting and filling, cutting and filling. You're not carting soil from one side of the field to the other. You can see here there's a couple of drainage flow paths that have been calculated by the software. It's filled an area in here and cut an area there to get our minimum grade also here. Now the software does that automatically. It works out the best way to do the earthworks to minimize the earthworks. Okay, so if we look at the earthworks to achieve this job, we're looking at 7,500 cubic meters or 9,900 cubic yards. That averages out at 56 cubic meters per hectare or 30 cubic yards per acre. At $3 per cubic meter to do the earthworks, we're looking at $22,500. Now since we've done this job, we've found out the earthworks costs are a lot lower per cubic meter or per cubic yard because we're just doing that cutting and filling that I mentioned before. Okay, if we look at the survey and design costs, roughly $3,300. So the total cost of this solution is $26,000. So if we calculate a payback period, we've got a cost of $26,000 and a benefit per year of $32,000. That gives us a payback of less than 1 year, which is quite impressive. And this supports a lot of the findings that we've got, where surface drainage improvements like this have the highest return on investment of any precision agricultural investment that you may make. Now, Nev Boland, the owner of this operation, was kind enough to capture some video of the earth moving operation. You'll see that this bulldozer has 2 GPS antennas on it for machine control, and it's shifting quite a bit of soil from cutting off those high spots and dropping them into the low spots. So that's the 4-way design case study. I hope you found that useful. Put some comments down below if you've got any questions. Now, what really excites me about this 4-way design service is that it opens up hundreds of millions of acres of dryland agriculture to improve surface drainage. It just wasn't economical to do with laser grading. Can you imagine trying to follow this design with a laser? It's impossible. But GPS allows you to follow this complex 3-dimensional surface with ease. And this technology is helping farmers continue their great work in feeding a growing world population, while at the same time boosting their income. Well, that just about wraps up our training. Before you go, I want to give you a word of warning. When we started to put OptiSurface out in the market as a way of improving land grading, I was surprised at the negative response I was getting from some quarters. And these were often, earth moving contractors who have been in the game for a long time, and also consultants who'd been doing laser grading designs for a long time. I couldn't understand why these people were looking backwards and not forwards. And then after a while I realized most of the benefits of this technology go to the farmer. Earth moving contractors who have been shifting a lot of soil with lasers don't want to go out and buy new GPS equipment so that they can win work where the earthworks drop by 50% or even 80%. And consultants are similar. They don't want to go out and buy new software to offer this service or risk their reputation on a new technology. However, in both these camps, contractors and consultants, there are forward-looking people who do understand that this technology opens up millions of new acres to land grading. These are the innovators. These are the ones who look for new technology. These are the people that are going to get the jump on this opportunity and take advantage of this new technology for the next 30 years. One more word of warning. There are some companies out there trying to imitate OptiSurface. However, our patented technology is unique, and the imitators' offerings have serious limitations that prevent you from getting the full advantages of GPS landforming. These companies pretend and even believe they have the same capabilities as OptiSurface, but they are really novices in this area, and it ends up costing you. Their limitations only become obvious after it's too late and you have purchased their equipment or services. We farm too, and understand the needs of farmers and work closely with farmers to get the best outcomes for them. So to help you navigate the maze of GPS landforming, over the last few years we've been quietly putting together a global network of over 200 earth-moving contractors, consultants, ag machinery dealers and precision ag dealers. They can help you unlock the full potential of GPS landforming and get started off on the right foot. If you're interested in this service, please click the button below and we'll take you to a page where you can learn more about what we offer. Remember, if you've got any comments, please put them in the input box below. Thanks a lot for watching. I hope you've enjoyed the training series. Best of luck with your farming and GPS landforming endeavours. Feel free to contact us at any time.